So I want to start explaining this by going back to this one. Okay. Can you see this? Can you see how the formula was derived? Okay. We don't need it, but I want to quickly explain something, and I'm going to have to refer to this. You see, when we talk about the least square regression line, this is what is happening. We're actually trying to find a line that minimizes the distance between the regression line and every other point. For example, this is our x1, y1, x2, y2, x3, y3, x4, y4, and so on. This line will be drawn such that the distance between the line and each of these points is the least. That's why it is called the least square regression line. Okay? Now, it is derived this way. Of course, we don't need to worry about this. I'm actually trying to explain something. I can send you this if anyone wishes to. You see, all these distances are D1s, D2, and so on. Okay, so the distance between this line. You see, this distance is on the vertical axis because what we are trying to do today is the horizontal distance being minimized, and I'll tell you why. Are you with me so far? Okay, great. Now, this vertical distance, this is on the y side. So how do we get the point here? If this line has equation ax plus b, this point here is ax plus b, definitely, right? For the x1. So this point here is ax1 plus b, isn't it? This point here will be ax2 plus b. This point here will be ax3 plus b. This point here will be ax4 plus b, and so on. Because any point on this line is ax plus b. And remember, x varies. So it will be axi plus b, right? Now, this point, however, is your y1, y2, and so on. That was why our distance is yi minus axi plus b. Okay? So we're trying to find a and b such that this distance, d, which is the sum of the squares of the distances, can be at the least possible value. Okay, and it was derived, you see, letting this to be I. If you open this bracket, you can rearrange, and if you let this to be I, because this is the one that can be iterated, so this is the ones with the I's. This is the constant, just leave it alone. And it continues, we don't need to worry too much. Then the quadratic thing that we did comes in here. For this quadratic equation to be minimized, it will be minimized when b is equal to this. You can just differentiate in your mind. If you differentiate this function, your minimum happens when the derivative is equal to 0. Do you agree? And the derivative will have been what? 2bn minus, we are differentiating with respect to b. B is like the x in this case. Can you say b squared? Hello, talk to me, please, if you understand. I want to be sure a lot of people understand what I'm saying. Do you understand what I'm saying so far? Take this like a quadratic equation. B is like your x. So if you differentiate, this will be 2bn. This will just be 2 times this summation. Do you agree? And this will be 0 because we are differentiating with respect to b. Why did I bring in differentiation? One sec. In our IGCSE class and even the IB class, you must have, no, I don't think in your time there was no differentiation in the syllabus. So I didn't teach in IGCSE class. To find minimum, we only used lists, completing the square, isn't it? We use the completing the square approach. But completing the square might be too difficult to observe in this case. So again, we're trying to find d, the a and b, such that this d, which is the summation of all the di's, is minimized, which is the summation, the distance between your y and your ax plus b. So that would be the summation. This is squared, of course. Yi minus axi plus b. Okay, which you can rearrange here. If you open this bracket, it becomes axi minus b, isn't it? So that will be yi minus axi then minus b. So all this could be a group, something like that. Okay, and that is what happens here so far. Now, if we let this to be some UI as it was done there, it doesn't have to be you can do whatever you call it. So if this is your UI, so our UI is yi minus axi, I from 1 to n minus b, and we open this bracket, it's going to be the summation ui squared minus 2uib plus b squared. Am I making sense? And if this is open, remember the iteration is I from 1 to n. This does not have any I, so it's a constant, isn't it? This b is also a constant. So if I open this, it's going to be summation ui squared minus, the constant can leave. I'm sure you still remember the property of the sigma notation. Okay, so this looks like a quadratic equation in B, not in X. Are you with me? Now, because this does not need any summation. Okay, because summation of A as I increases is still just going to be NA anyway. So you don't need anything. Okay, is a constant. So it's like saying the addition of B when I is from 1 to 3. When I is 1 is your B, when I is your 2 is your B. So it's just going to have your NB. Maybe I can include it because I have to include N at some point. One sec, please. Okay, got it. It's here. So this is, let me include it first. Summation of B squared, isn't it? Everything is I from 1 to N. So when your N is 1, it will be squared. When I is 2, it's still B squared. When I is 3, it's still B squared. So at the end, it's going to be NB squared. Do you agree? So we can then rewrite this to look like quadratic, actually. That's the whole point. We can then rewrite this. Taking this first, that would be our NB squared, just like your quadratic AX squared. Okay, then the second term could be 2. Remember this, something like this. So that's like your BX. Hello, are you with me? And this does not contain B at all. Okay, so actually I shouldn't write this way, I should write this way. I'm just trying to show you the X. That's why I'm writing this way. Okay, the constant, which does not contain any B, will be here. Does this make sense so far? So what we are trying to do is, okay, we are trying to talk about the minimum of this. We are trying to find A. The whole idea is to find A and B such that this is minimized. So that looks like quadratic. So how do we find the minimum of this quadratic? When do we have that minimum? What is B when it is minimum? That is why we can think of either the completing the square, which might be complex to do because of this. Actually, shouldn't. We have to first factorize n. Do you agree? You have to first factorize this n out. Hello, do you remember completing the square approach? If you have ax squared, plus bx plus c, you can first take this out. You have x squared plus b over ax. Remember that? Then you can have your c, blah, blah, blah. But rather than do that and trying to find what to add, what to subtract, we could just apply the differentiation. So if you differentiate this will be 2b, right? The derivative of b will be 1. Okay, so if I call this, let's f of b be what you have in the previous section. You have nb nb squared. Then the second term is minus 2. I'm going to put this together for obvious reason of b, okay? And the last one is plus the summation of ui squared, I from 1 to n. Of course, this is also I from 1 to n. This I from 1 to n has been evaluated to be n. So if we find the derivative with respect to b, it will be 2nb or 2bn, okay? And this will be 1. So we are left with 2 summation ui. And this is 0 automatically, so no need to appear. Okay? Are you getting it? So at minimum, remember, is that stationary stuff. This derivative will be equal to 0. Are you with me? In that case, it implies that, you see, there's not much to do today. I just needed to understand this concept to understand the last concept. So we have that such that 2nb minus 2 sigma ui would be equal to 0. And if you want to make b the subject, this goes away and you divide. 2nb is equal to 2 that, then your b will be 2 sigma ui divided by 2n, which is more or less sigma ui divided by n, isn't it? And that is simply 1 over n. So we can say 1 over n sigma ui. This is like your u bar. Do you agree? This is like u bar. Okay, but because u is not just a variable, u consists of other stuff. Remember, u from here is this yi. So that is sigma of yi minus axi. Okay, no, divided by n, sorry, not 2. With this, you can open again. Remember, you can write this as 1 over n sigma yi. Then a is a constant, isn't it? 1 over n again sigma xi. So clearly, your b is equal to, from here, from 1 over n sigma yi, then a 1 over n, so maybe this could be like this, xi. Clearly this is x bar, this is y bar. So that is why we say our b is y bar minus a x bar. Okay, I just wanted to explain that part because it looks a bit confusing. Okay, but the other parts should be easier. Any questions, please? So we've been able to, with this, what is my control? 1 sec. So this is, I just wanted to explain what happens here. Okay, I just wanted to explain what happens here. The rest is easy. So the rest is just by substitution. If you substitute b into the original expression, remember from here, from here or here, then you can have this back, you can expand, okay, and you get this. This is the quadratic equation in terms of a, then you can apply the minimal stuff again. Okay, I wouldn't want to do that, but you understand what I mean. So this looks like quadratic equation in terms of a. Differentiate again. If you differentiate again, this will be 2a with this term, right? This will be 2 with this term, okay? And this will be 0. And at minimum, the derivative will be 0. If you equate what is remaining here to be equal to 0 and make a the subject of the formula, this is what you have. So this is what our calculator does for us. Okay, so when finding the regression line y on x, we are actually trying to find the line that represents this point, taking the vertical distance to be minimal. Does this make sense? So, but in today's case, we are going to be discussing the regression line, taking the horizontal distance to be minimal. Now, you might be wondering, why is that the case? What's the difference between the two? You see, in some cases, remember, this is your independent variable, this is your dependent variable, right? We can use the value of X to predict Y. Okay, we can always use income to predict this. And that is because our X is more precise. Somebody's income is a precise data. We can actually measure that correctly. But grocery bill, maybe not. If I ask you now, how much did you spend last time you went to Samuel? Who remembers how much they spent last time they spent in Samuel? Do you get my point? But if I ask you if you're a worker, how much did you earn? You can always tell me how much you earn. So some data are more precise than the other. So in the previous section, what we have done as at yesterday is to use data that are more precise to generate the other variable. In this case, our X is more precise. Our Y is the one that could not so sure. Hence the reason we are minimizing the error on the Y-axis. But in the other case for today, let me go back to that point. I hope you can see the book here. You see, here we are interested in minimizing the horizontal distance. Okay, look at this line here. This means that we can minimize the horizontal distance of the point from the line so that all error is associated with the explanatory variable. All errors are associated with the independent variable or the X variable. I don't want to call it independent variable this time because the old label will change. Why do we say errors will be associated with the X variables? In this case, Y is more precise than X. So X is not precise, unlike the other one. If you do not really know how much you spend in Samuel, you can actually give me an idea. The idea you give me will have some errors because that's not the actual. I spent about 23 mop. Maybe you actually spent 20 mop and you don't remember. Maybe you spent 19 mop. Maybe you spent 28 mop. But you remember giving them 50 mop and they gave you back 20 mop and some change. But you don't know exactly how much. So there's some error there. Okay, so in situations where the error is associated with X, we will be discussing X on Y, not Y on X. Because Y, which is more precise, can then be used to predict X. In that case, our equation will look like this. Since Y is more precise, Y will be the one to look like our independent variable here, and X will be depending on Y. Let me show you an example. Look at this one. Feed a number of eggs. It's very tricky because it's already X and Y. But to find the regression Y on X, in this case, will not be that good. Because what is the whole point of finding the regression line? In order to be able to predict something when given the order, isn't it? Let me go back to the board. Not yet. Can you see the board? Not yet. How about now? So when you have Y equals AX plus B as the equation, if X is precise enough, you will get a more accurate Y, yes or no? But if your X has so much errors, how can then your Y be reliable? If X itself is full of errors. Do you understand? Okay, so in that case, if Y is more precise than X, you do the equation X equals AY plus B. Okay, so if the data for Y is more precise, you do the equation x is equal to this. This is called x on y. This is the regression line y on x. They are two different things. If you're able to establish this, so if someone tells you y, you can get x. If someone tells you the x that was derived, you can get y, then that y will be more reliable. It doesn't mean that when you have the regression line x against y, only y will always be given. No, x could be given to predict y. But you have used the data that was available, the data in your bivariate table, like this. Okay, you have used this data to generate a model. And since your y is more precise in that model, you can really, you can really trust to a more certain extent whatever x generates for you, because you use a more precise data, y in this case. Am I making sense? Now, in the case of the feed question, in most of your question, it's been said clearly, y on x, x on y. It's been specific. But what if it's not specific? Then you have to think for yourself. It's probably going to happen maybe 5 or 10% of the time. It's not something that is common for you to be put in that state of dilemma. Oh, which one do you do? Now look at this. It says, explain why it would be appropriate to use regression line of x against y. Feed a number of x. The data says, this data below shows the quantity of feed eaten. How can you measure the quantity that was eaten by, maybe chickens? Do you understand that? It's not going to be a precise data. But what about number of eggs? Can you approximate the number of eggs? You can always count the number of eggs that were laid, isn't it? But this decimal, they were just approximation. Maybe there were some 0.00011 something, which the scale wouldn't show for you. Am I making sense? And if you take the feed into the whatever container you use in the farm, what happens to the remaining that the chicken, the little grains that the chicken are not eating eventually? There will be something, isn't it? Doesn't mean they do not have their weight. Do you understand? So that data, you will see that this is a more precise data. And if this is a more precise data, then that should be your explanatory variable, while the other should be your response variable. Am I making sense? Let's play this and see. To find this regression line x against y, y against x is not difficult. It's just, I just have to change something in your calculator. I'll tell you in a bit, but I need you to understand the background. That's the whole point of this explanation. Understand? Okay, so let's play this. Let me make sure I'm sharing my audio. Okay, I think I've shared audio. Give me thumbs up if you can hear what it says. One sec. There we go.
In previous examples, we have used linear regression to find a linear model for the dependent or response variable y in terms of the independent or explanatory variable x. The least squares regression we calculated minimized the vertical distances of the points from the line, so that all of the error is associated with the variable y. In an experiment where the y values can be more precisely measured than the x values, it may be appropriate to use the regression line of x against y. This means that we minimize the horizontal distances of points from the line, so that all of the error is associated with the variable x. In this example, the x values are the quantities of feed eaten by chickens, and the y values are the number of eggs the chickens laid. We can count the number of eggs laid exactly. However, the quantity of feed eaten by each chicken will not be measured as reliably, because some feed will be scattered or spilled. Since the y values are more precisely measured than the x values, it is appropriate to use the regression line of x against y. On a calculator, we use the same procedure for this line of best fit as for the line of best fit of y against x. However, we need to swap the two variables, so y becomes x on the calculator and x becomes y on the calculator. So, on some calculator models, it will look like you need to write down y equals ax plus b, whereas you actually need to write down x equals ay plus b. You must be confident that you can do this procedure correctly. Having calculated the regression line, we can use it to make estimates about the variables. First, we estimate the quantity of feed required for a chicken to lay a dozen eggs. We substitute y equals 12 into the regression line and evaluate the answer. We would expect that 1.76 kilograms of feed would be needed. However, this may not be reliable because it is an extrapolation. We next estimate the number of eggs laid when 1.2 kilograms of feed is eaten. We substitute x equals 1.2 into the regression line, then solve the linear equation for y. We would expect about 8 eggs to be laid. This estimate is likely to be more reliable because it is an interpolation.
Does this make sense? Now, I want us to use the calculator so I can show you what you need to change. And luckily, I have one of the SON calculator with me. So everyone, just put in this number in list 1 and list 2, just like we did yesterday. I may not be as fast as Nakita. Oh my gosh, she was so fast in the class. Let me see if I can beat your record, Miss Coffee. Okay, I give up. I'm not competing because you're the boss. So with this, actually, that's all about regression and correlation. So lucky you are just to use calculator in your exam. So there's no need to waste so much time. There are 12, okay? Always check your data, please, because sometimes you might put in the wrong stuff. So when you put in your values, you double check before you proceed. Okay, I think I missed something, because one is 11 and one is 10. So this is where we should double check. 0.57 and 4, 0.86 and 6, 0.49 and 3, 1.37 and 9. Okay, I wrote 6. I knew it. This one and 6. Okay. 0.5 and 3. 0.97 and 6. 1.06 and 7. 1 and 7. 0.68 and 4. 1 sec, please. 1.34 and 9. And finally, the last one and 6. 6. Okay, so are we there? So all we have to do is go to, what is the first thing we always do anyway after we put in that? Is that F3? No. Exit. Okay, go to that set. Is it set? Where you change your list 1 and list 2. No, not you. Are you there? Okay. 1 sec, please. I think I used something wrong on this calculator, so I'm trying to find. Okay. So entered. Okay, yeah, I'm there also. Okay, so if you go to that set, you see, this is what you should have right now. Can you see my calculator? Can you see this? See, it comes with list 1, list 2, right? The only thing you have to change is change the first one to list 2 and the other to list 1. That's all you have to change. Okay, so change it. You know how to change it, right? So if you click on F1 list, it tells you list. The first one you type 2, and the second one, F1 list again, you type 1. So tell me you have this. Does everybody have this? So go back to your table and do the normal stuff, the same way you do your regression line. Make sure you have this. So at the end of the day, your, what is it called? 2 variable, of course, because we are dealing with bivariate data, so we are only concerned with 2 variable columns. Okay, we are not dealing with a single variable. So 2 variable column, X list, list 2, Y list, list 1. Once you have this, we are good to go. So now that that is done, regression, you should have, what do we have? Oh no, I pressed something else. Regression, X. Okay, your X means you are dealing with a linear regression. Okay, that's what that X stands for. X squared is there. That's not what we don't need that. Okay, I'm sure this is what you do. And your AX plus B. So do you have the same number as it is in the book? So the only thing you change if you are dealing with X against Y is to enter the data the way it is and just change list 2 to list 1, list 1 to list 2, that's all. Because there's a past question, or maybe in one of the worksheets that I gave you, is asking for Y against X and X against Y. So you don't have to enter this twice. So if you are doing Y against X, it's going to be in that order, list 1, list 2, provided you've entered it as X and Y, list 1 in the table. Do you understand what I mean? So you just have to change it to list 1, list 2, list 2, list 1, and that is it. So when you're writing, remember at the bottom it says Y equals AX plus B, right? 1 sec. There's a reflection. I hope the reflection doesn't affect what you can see on my calculator. Can you see my calculator? You see, at the bottom, you have Y is equal to AX plus B. Please ignore that. So in your mind, you are working with X is equal to AY plus B. Are you with me? So you ignore what Y is equal to AX plus B says, substitute your A and B and just write the equation. And that's all you have to do. Does this make sense? So that's all about regression line, Y against X and X against Y. So I want you to attempt this question. Everyone attempts, I think it's in the worksheet. So maybe I project the worksheet instead, because this is like in 2 pages now. So I was able to find 2 past questions, then I put some questions from your textbook just to make it sweet. So you don't have to think you don't have enough food to eat on the paper. We have enough regression food. Okay, so look at this. Everyone attempt question 1. Oh, let's discuss A together to save time. Look at this. The table below shows the amount of time a sample of family spend preparing oatmeal meal each week, and the amount of money they spend each week on fast food. Explain why it would be appropriate to use regression line X against Y in this case? Who wants to go first? X against Y, not Y against X in this case. Come on, anyone, quickly. Do you want me to show you the previous example? If you want me to show you the previous example, raise your hand. Okay, no one. So that means you can attempt this. I'm waiting. Explanation. Why will it be appropriate to use regression line of X against Y?
Is it because for time on homemade meals, you may not always like be recording the time, so it's going to be an approximation.
Okay. So what you need to do is focus on the precise one, not, you can focus on the precise one first.
Oh, okay. For money on fast food, you can always just look at receipts.
Exactly. So you can always get, like money on fast food is a more precise data than the time spent cooking, isn't it? Like, oh, because it's easy to, keep track of money spent on fast food because you can always just collect the receipt over time, isn't it? If you want to get that precise, you can always get the receipt over time. However, time on oatmeal stuff is just going to be an estimation. It will be less precise than the money. We are not saying both of them will be precise. We are not saying one is perfect, but we are looking at one that is more precise than the other. I showed you an example earlier regarding, it has to do with money spent as well. Was it in the case when I said Samuel? It's because the other data is less precise than that one. Okay, and now the money spent in a place like Samuel is now more precise than this one. Okay, let's look at the other one. Look at this. Which regression line should be used to model this relationship? This is where the confusion can be. Is it X on Y or Y on X and Y? Anyone? This is the table that shows how far a group of students live from school and how long it takes them to travel there each day. Distance from school and time to travel. Hello? Distance from school and time to travel. Can anybody else reply? Not Ethan Cheng, because he's trying to reply again.
It should be X against Y because Y is the more precise one.
Y would be more precise in this case. You can always, time yourself, right? Can always check your time. But distance, are you going to move around with tape rule or meter rule? Okay. Or, okay, now you're living in White Choy Garden, where I first lived. You plan to go through the center of the park, and you got there, and due to the COVID, the gate has been closed. You have to walk around. You see, you can't really say. Do you understand? Even though we have technology that will tell you have walked 3 kilometers, 4 kilometers, but are they really precise? Do you understand? So one will be more precise than the other. In this case, your time will be more precise than the distance. So since time will be more precise, the time should be your independent variable this time, and X should depend on Y. So it will be X against Y this time. Does it make sense? So to answer, just focus on which one is more precise, and you can shed some light on why the other one is not as precise as the other one. That's how you explain. Okay, look at the example that we have just shown each other. Look at the explanation. The number of eggs, you see, the whole thing started with which one is more precise. That's the trick here. Oh, the number of eggs laid can be counted exactly. However, the quantity of feed cannot be measured exactly. Okay, something like that. Oh, simply because there will be some that will have been scattered all over, spread all over, some left over by the chicken. So you can't really measure, the quantity of feed that was eaten by the chicken. Because as they are all rushing to get the food, chicken are also, they are so foodie, even more than some of us here. As everybody's rushing, every chicken is rushing to get the food. Maybe they just spill the thing over on the floor and they're eating it on the floor. But does that mean everything is accounted for? Even if you measure 1 kg, does it mean all the 1 kg was consumed by the chicken? Okay, so you can just give this, this can be accounted for, and this cannot be counted for. So as a result, the number of eggs, Y is a more precise data than X, which is the quantity of feed or the amount of feed taken. So that is how you explain it. Does this make sense? All right. Now let's look at what a past question looks like. So these last two are past questions. The following table shows the marks scored by 7 students on 2 different tests. Test 1 is this, test 2 is this. Here, they are not asking you which is more precise because we don't even know, both of them are tests. So whatever error should apply to both of them. That is why the question was not raised. Line 1 is the regression line X on Y. So this is what I'm trying to say now. Line 2 is the regression line Y on X. So you are not going to enter this data twice. This is X on Y. Once you enter the data, X in list 1 from the beginning, Y in list 2 from the beginning, all you have to now do is change them when it is time, okay? And change it back again. Does this make sense? So find A and B. You have to find A and B. You don't have to write X is equal to 1.2 plus X, Y plus 4. A is equal to 1.2, B is equal to 4, something like that. Okay, but if you write the whole equation, IB allows that as well, but just focus on A is equal to this and B is equal to that. That's enough. Okay, then L2 is the regression line Y on X. So which means go to the list variable stuff and change it back to 1 and 2 this time. And again, write down X and Y. Okay, Jennifer was absent for the first test but scored 29 on the second test. Use the appropriate regression line to estimate. This should be mark. This should be mark. Anyway, to estimate what Jennifer will get in the first test. Which one do you think is appropriate this time? Remember, you have found the two X on Y and Y on X, which would be more appropriate to be used. Both of them are tests. Anyone?
X and Y.
Why do you say that?
Because she can't measure her first test and she can measure her second one.
Exactly. Oh, I thought the first was given. She was absent for the first, so that cannot be measured. But she was there for the second. So you have to use the one where the second test is your, where Y is your dependent variable. Well, where Y is your independent variable. Do you understand that? So you have to use X on Y. So if it is X is equal to, from here, X is equal to AY plus B, that Y value is known as 29 here. So, and remember, all the Y values gave you what A and B are. So it will be more precise to get X from L1. Do you understand? Because Y is given. Okay, and then there's another one that has to do with that. Is asking somewhere, another student, you see, by finding the equation of an appropriate regression line. They never told you either T on S or S on T. So you will be the one to think which will be more precise, which will be more reliable. So estimate the time Jasmine spent on social media. if the self-esteem is 29. So you have to be the one to decide, T on S or S on T. You think about that. This will be part of your graded task. So I will give you 5 and 6 and maybe one of these. I'll put them in 2 pages. I'll call it graded activity like the previous one, and that is what you will return back to school. The rest, please practice on your own. Any questions, please? Nope. Okay, so let's keep practicing. This is all about regression analysis. Let's us see where we are. Topic 4. That's the end for today. I'm just going to quickly show you. So we are okay with all this. You can see the Y and X are actually separated from the rest. I don't know why. So here we are okay. This is what you are expected to know. Students should be aware that they cannot always reliably make prediction of Y from a variable X when using X on Y. You should know that as well. Okay, and I think the same warning was given in the previous one. Okay, you should be aware of the danger of extrapolation that is not fully reliable, that they cannot always rely on making a prediction of X from Y using Y on X, something like that. So these are just things that you should know. Technology should be used to find the equation, so you are not expected to know all the old stuff. And for this one, positive, negative, strong, weak, no correlation, you should be able to distinguish between them, and causation as well. So I think all this we have covered. Okay, all this we have covered. So with this, we are done with regression and correlation. Random variables will be the next districts, and the last will be the continuous random variable. I plan to do some of the districts within, tomorrow is Tuesday, right? Tomorrow is Wednesday, yes? Oh no, holiday is almost over. Oh, I don't want to go to school. It's okay, I want to go to school because I want to see your faces. Yeah, Karen, yeah, you can look like that. You're coming on Monday, don't be lazy. All right, guys, if there are no questions, I can stop the class at this point and I'll send you this worksheet consisting of 5 problems, or maybe 6 already. Then I will send you a modified one with space that need to be returned back to school later. Okay, I hope everybody saw the one I sent overnight for the previous topic. Okay, please keep practicing. This is not a difficult topic. The more practice you do, the better. Thank you very much. I'll see you tomorrow. Bye-bye.